Assalamualaikum warahmatullahi wabarakatuh. Very good morning to everybody. Salam sejahtera. Thank you to Dr. Mahendran and to the committee for inviting me to speak against my better judgment. Okay. Today, as was mentioned by Dr. Mahendran, my talk is on directions of statistics in hydraulics and hydrology research. When I was given this topic, I wasn't really sure what I was going to talk about. And I was thinking about it essentially about last week. And at that time, I have a nephew who is now, I think, about 16 or 17 years old, and he's very keen on the universe, looking at worlds, astronomy, things that explode, looking at Google Earth. And he showed me something very interesting to me last weekend. He showed me space noises. In the YouTube, he likes looking at YouTubes and seeing strange things which happen. And he showed me the 5 most mysterious sounds recorded in space. And it's something which I think for people who are working in hydraulics should try and look at. I know it's of things which are new. Because it brings us to something, how do you say, a little bit out of our normal work experience, but something which, when I saw the video, related very much to statistics and to hydraulics, because hydraulics is not just about water, it's also about the atmosphere. The only thing is that the atmosphere has a very, very low specific gravity. Yeah. But essentially, similar things happen, both in the atmosphere as well as on the Earth. And what we see is that now, especially when the space exploration is showing us new things about what's happening in other planets, we start to see that what we see in waves, in water as waves, are similar to radio frequencies. And what people are now measuring, because they're now able to send out spaceships out into a space, is looking at the radio frequencies or the noises, similar to what you would listen in radio, but at a low frequency, very high energy type of waves coming up. And once you have anything which has a frequency or a wave, you should be able to start to analyze it. And people have to identify why these noises are coming. And you will see, I think, if you've looked at a television series, some of the television series try to look at aliens or other life. I mean, people now are searching for other life in planets, looking for the existence of water, the possibility of any type of life, a new alternative Earth. I know, and people are coming with all sorts of new theories to try and think what's happening. But these are the sort of things which are really right at the cutting edge of science. And this is something which I think, as young scientists or even older scientists, should try to think, what are these? Are these the same type of sounds you would hear in the night in the jungle, in the village, crickets? Are comets alive, screaming as they run through the universe? What actually creates these sounds? The people are investigating a lot of these weather features, the movement of gases in planets, which are really hydraulic features. Look at the meanders of waves. You'd actually see this if you look at chimneys emitting smoke. So pulses of electromagnetic energy propagate out into space. And many of these type of data is actually available differentiate between hydraulics, hydrology, and statistics, but essentially almost all of the hydraulic phenomena have to be explained through mathematical concepts or statistical concepts. And these types of studies are being done, by the JPL, the Jet Propulsion Lab, NASA, MIT. I'm sure any of you are statisticians, people looking at time series. Immediately you start to see these frequencies, you start to think, well, what is the pattern? What is the beat? Is it random? Is it white noise? Is there something consistent inside there? So this was the thing he showed me for the space. And then, of course, because I'm an oceanographer, and he was very keen on all sorts of strange noises, he then showed me ocean noises. Which is also very interesting here because you actually start to see some of the frequencies being shown, and the frequencies in the ocean are very, very long. And they're trying to tell us something about what's happening on the Earth. Just now we were out in space, in very thin atmosphere, but now we're looking at very dense, type of fluid. And people are imagining, what are making these noises? Are they some creatures? And some of the ideas of them are very interesting for us in terms of climate change. Because some of these noises, people think, are caused by icebergs scraping along the bottom of the ocean or along the sides of continents as they melt off from Antarctica. And these noises are being measured by an array of songs in the ocean maintained by the international community. And many of them you can just download for free. And you can get the spectrogram. So if we're having a lot of icebergs melting, is the pattern of iceberg melt, the pattern of these noises changing? We're supposed to be getting higher temperatures in the oceans, icebergs are melting. Over the time in which the sound has been recorded, are we getting increased frequency of the sound? Are they indicating that more icebergs are melting and scraping off the Antarctic shelf? Can we see the whistle of volcanic eruptions on the ground? Can they be a predictor of future earthquakes? Or tsunamis? I thought, yeah, that's very interesting. And actually there are some other videos which actually show the frequencies and actually show how it's been speeded up so that we can hear the noise, and actually show the real frequency, 1/16 times slower, and showing the actual spectrum of the noise. So this started getting me thinking, because recently I brought a bread maker and was looking at recipes and looking about how the bread maker is a robot cooker. You can cook almost anything inside it, and I was attracted to it, and so I started, and I bought one. And then I thought about, well, this bread robot cooker is like an artificial intelligence. We get washing machines with fuzzy logic, and they're really looking at now, when starting to think about, brought me to thinking about big data and the different methods people are using in deep learning, or another word now, the more modern word for neural networks, or artificial intelligence. But now people are looking even at machine learning, a different word now. And if we start to think about it, those of you here probably are very young. I remember when I was in university looking at this film, 2001, A Space Odyssey, and I encourage every scientist to look at this movie. This movie was made in 1968, but the ideas of the author, and especially of Arthur C. Clarke, who is a science fiction writer, is something that tells us, that imagines what will happen in the future. Many of these science fiction stories, science fiction books, are actually foretelling or trying to imagine what would be the boundaries of knowledge in the next 20 years. There in 2001, and this is 1968, and even previously people were talking about robots or machine learning and doing what humans could do, there was a heuristically programmed algorithm computer, HAL 9000. You can look this further up in the Google, but HAL had one red eye, and it used to focus its eye on everybody and look at what was happening. HAL was at that time capable of speech recognition, facial recognition, all the sort of things which people are now working on to make robots try to imitate or become more human. And of course, playing chess is something which many programs already can do. And really, we are facing now, and many of young people are journeying into the unknown. And we really should be looking at, for example, Star Trek, that space, the field of hydraulics and hydrology really is in the sense of final frontier, because we're going to the deep ocean where actually we don't know a lot about what's happening there. We're going into the outer space, even more we don't know what's going out there, but we're getting a lot of data coming back in. And both of these types of data are hydraulic data. They are hydraulics of water, or hydraulics of the atmosphere. They are hydraulics of liquids, any type of liquids. You see, your continuing mission, everybody in this room, is to explore strange new worlds of data, to seek out new knowledge and civilizations, and to boldly go where no one has gone before. But how do we do this? How do we look? As Dr. Hafizan has mentioned, looking at patterns in data. But more important to us, why are we doing this? What is the link now between big data and statistical analysis? And there has been a big confrontation between people working with big data and saying, I don't need to do statistics, I've got so much data. And people from statistical analysis background saying, you're not doing the statistics right for the big data. What really is the science behind it? What are the causal relations? And this is the most important thing for statisticians to always remember. Maybe I can find a relationship between A and B, but is it meaningful? Is it something causing one another? Or is it just the birth rate and the number of bananas eaten are correlated together? I know. What is it one got to do with the other? Maybe it's just the number of people increasing, so more people, more bananas being eaten, rather than a direct relationship. So we need to be able to remember back our basic laws, the scientific laws and the laws of statistics. Have to go back to research and the basics of research, understanding to observation, testing and the scientific method, but also to remember that some discoveries are made by chance, for example, Alexander Fleming and penicillin. But it was through his persistence of repeated experiments that he found this. Thomas Edison, 99% perspiration and only the 1% of inspiration. So you really do have to work hard because there's so much data there to be tested. So what is some of my listing of where we should be going in the looking at big data, hydraulics of the atmosphere of liquids? Here, you need to be a fast learner, and I can't say this enough because yesterday I thought that last week I thought my paper was in the afternoon at 2 o'clock. But I came in this morning at about 8 o'clock and found that I was giving the paper at 10:30. So I had to very quickly, within 2 hours, finish up my presentation. Okay, so you do need to be that, because there's so many new methods coming up, so many papers coming up. You have to be on the ball to try and learn new techniques. 2, don't do it all yourself. So many people have already done certain things. Learn from them. Stand on the shoulders of giants. You have here people, Dr. Mahendran, Dr. Hafizan, Dr. Zaharin, who already have that experience. So learn from them. Go further. Because if we're starting from zero, it will be very difficult for us to become the giant. So that's why we have to be a fast learner. We have to find the giants and learn from them. 2, most importantly, is to ask the right questions. And I can't say this enough, because I know probably many of you have not heard this book. I had this when I was doing my PhD. It was a book which was read on the BBC. You can actually get this downloaded, Hitchhiker's Guide to the Universe. I think it's It's written by this guy, Douglas Adams, but inside there was a super to the nth computer called Deep Thought. And it was created in order to calculate the answer to only one question. Deep Thought was a special computer, the size of a small planet. Actually, it was Earth inside the book. So Earth was created to find the one answer to the one question. The answer to the ultimate question of life, the universe, and everything. Okay? So that was the whole purpose of the supercomputer Earth. And it took 7.5 million years in order to do the calculation. And the answer is 42. But nobody knew what the question was. You know? Okay, you have to read the second part of the book where the question actually came up. What do you think the question was? The answer is 42. Come, I have mathematicians inside here. Oh, I must give them a fail, Dr. Mahendran. Well, I'll leave that to you to find out what the question really was. But that's very important. I think a lot of people are doing things with data, but might get an answer, but the answer may not be the answer. Well, it would be the answer to the question, but maybe you're not asking the right question. So that's very important. For example, now a lot of people are thinking, Shakespeare is a very important playwright. Maybe if we have a whole room of monkeys in, there would be the chance that the monkey could type exactly. It's probable, isn't it? Out of all the probability that one monkey would be able to type all the works of Shakespeare, very famous playwright. But why are we asking this question? I mean, what would be the benefit of getting by probability, by chance, this infinite monkey over time would be able to produce Shakespeare? So we have to really think about what all this big data that's coming in, that we're working with the data, what actually are we asking? Why are we asking this question? So especially for the young scientists now, this is very important to make sure you're phrasing the right question before you start your research. The next thing, of course, once you start to ask the question, what is the right method? And this is very interesting. If you're a scientist working on data, you need to be able to go to this site, KD Nuggets, and this site is for data scientists. They did a poll to ask what are the top algorithms and methods used by data scientists, and this was their results. This is the result of the poll, which was recently done with N844. Okay, most people choose regression. I think it's almost automatically everybody will say, what's the relationship between this and this? But we start to see the list of methods which are being used. Yeah, recently the first paper we're talking about PCA. We talked about decision trees. There was clustering and regression. So we're right in there. How does this method how is it biased by who you are? And we start to look here. Industry is the blue line. Now, the industry likes to look at visualization. They like to do time series. And governments like to do a lot of visualization because they have to give information to the public. So they like to do a lot of infographics. And here is academic. I'm sure here, academics, a lot of you apparently are doing deep learning. Artificial intelligence, neural networks, AHP, all sort of academic research stuff. But this is really very interesting because we have to look at, for example, if you want to go out into industry, what would industry be thinking of doing? And probably industry doesn't do deep learning because it's taking a lot of their resources. So they want to go and do something more, easier or simpler for them to do. But this is very important because we start to look at government, looks a lot of principal components analysis and does a lot of science series because they have a lot of data over time. Weather data over time, river water quality data, flow data is all over time. So a lot of hydrological data is over time. And a lot of hydrological data has to be presented in a visual format. And where do these people come from? Well, we're not too bad. Asia presents about 20%, 18% of the people who are being polled. But of course, most of them come by any poll, why you think that this in a way is skewed? Why are most of the people in the US and Europe? Well, maybe they have more scientists on the internet willing to answer the poll. So in a sense, you might say, is this being biased or not? So these are one of the examples of when you start opening up a poll, it depends who's going to or will be willing to answer your question. Here's about the affinity of the algorithm, where we look at more academic algorithms and more industrial algorithms. And we see here that most of the industrial algorithms list around here, whereas the academic algorithms tend to fall in this type of grouping. So where do you think the methods that you're using, where are they falling in? Who are the people that you want to try and engage with? Is it industry or more of the academic people? The other thing is big data is here to stay. So we do need to use it, but it's not so big now as it was 2 years ago. I think about 2 years ago, a lot of people were talking about big data and what to do and what the methods were. But in a recent report about technology use, the Gartner 2015 Hype report, especially if you're looking of going out into industry to apply your skills, we start to see that machine learning is the new in thing. So those of you who are starting out in your PhD, maybe you need to think about how you're going to apply your methodology later when you want to get work towards machine learning. Here's the curve for 2014 where we see big data here is almost at the peak, but people are starting to get disillusioned. And here we see where most of the productive work was being done, speech recognition. 3D scanners and 3D printings were all the in thing in last year, but 2 years ago. And this year, we see machine learning is coming up. You know, and this little, in the next, what does this mean here? What will happen in the next 2 years in the open circle? In 2 to 5 years, you'll reach the plateau. You're almost at the top, then people will go down. So really, you want to reach here. If you're going to go be relevant in the next 5 to 10 years, you want to reach these blue dots. These are all the up and coming things. And look, in more than 10 years' time, people are looking at smart dust. Some of these smart dust, people like to be able to imagine you have dust, which is intelligent, it has got sensors on it, and you just throw it into the room. And it can measure the temperature, the airflow, presence of people inside the room. It can tell you everything or sense what is inside here. That is expected to be the technology over the next 10 years and more. Okay? Quantum computing, brain computing, interface, but what has already reached the end of its life, you would say, or here now becoming going into the public knowledge. So here we're looking at the innovation, the start of research, and here we're moving into making the things commonplace, routine, into the public sphere. Okay? Just like enterprise, we now have 3D printing. We don't have it yet in Malaysia, I think, but overseas people are looking at 3D printing, and it's almost at the peak in over the last 1 or 2 years. But we see that a lot of work now is more or less focused into two ways in which people are approaching, looking and finding knowledge. One is machine learning, and this is the same as, I would say, the scientific method, testing something, training. But the other one is data mining, observing and trying to understand patterns, new patterns, or unknown things, previously unknown properties. And this is actually essentially the two parts, you would say, of statistics, because the machine learning is trying to do correlations, hypothesis, inferential, whereas the data mining is trying to observe and to see what's going on, trying to learn what the new things are. But the problem with big data is that you cannot hide anymore, because big data tries to predict everything about you. Anybody who's got a Gmail platform or is not on a private platform where all your clicks and things are not recognized, Google knows about you. Maybe they don't, they even know your full name, they know where you live, they know what you like, what you shop, what you buy, what you look at. Before, people wouldn't know you. You could menyamar, pretend to be somebody else, but now it's very difficult to do that, Yeah, 15-year-old labradoodle that likes cat food. And the United Nations also getting into it. In fact, they created in 2014 a working group on big data for official statistics. And they're trying to use this to see how the Sustainable Development Goals can be measured by using big data, so that you cannot hide or fudge your reports. But then you have a problem. Is this big data really dependable? Is it really, if the analysis of it really telling us what we think it's telling us? And a lot of people are thinking, big data is good, but we might be making some mistakes if we analyze it wrongly. So we need to take it with a pinch of salt. hati-hati. Yeah? So here we have some articles here which you can go to. 8, 9 problems and many more problems people are saying coming up with big data, because big data makes some certain assumptions. It thinks I have so much data, I don't need to worry about errors, and I assume that I have the total n is everything, but they forget n is only the people connected into the internet. N is only what you allow Google to take up. You see? So same like I said, the poll just now, there are some problems with some of the assumptions being made in analyzing big data. For example, you said how often a certain thing happens. We'll always have a relationship with something else. Whatever you ask, you can find a relationship. But is that relationship a causal relationship? Is that a reason? Is it meaningful? Or is it just something which we can just throw and find any type of relationship? And essentially in big data, you can find a relationship with anything. But they forgot about applied statistics in big data. So here, there are some, I will mention a bit later on, some of the items that, which are important to think about. But the other thing I want to say is that if you put garbage in big data, you will get the garbage out. And you will have the problem with data quality. And this is a paper which, comment which came out in 2016 about reproducibility, that a lot of data, a lot of studies sometimes fail to be reproduced. Well, last year, University of Virginia did a reproducibility project that repeated 100 experiments. So how many do you think of these experiments could be reproduced by them? Yes. 10. Anybody else? 40? 1/3. Okay, let's look. So some of you may have read this one. Only 1/3 was successfully replicated. Imagine 70% couldn't be replicated. That's a big number. Yeah, those statistics, no statistics, 10, yeah, that's very good. For myself, an environmental scientist, if I go to one place and measure, and I go back again, maybe I said 30% of the time I might get, 25% I might get back the same thing. So it depends what data set. Of course, you have the control lab experiment, you might expect a higher degree of reproducibility, but not so here. Why was this happening? Well, the study itself was criticized because it had its own replication errors, because it's one of that 100 also. Why? The comedian, John Oliver, said there is no Nobel Prize for fast checking. And actually, it's not unheard of that a Nobel Prize winner later on found that their original assumptions was wrong. You can try and find this on the Google as well. A case where the original assumption was this because of this, and then later it was found, oh, you asked the wrong question, and so you got the wrong answer. It was wrong. That's Nobel Prize winner. So really anybody can be one. What was the problem? The problem is we have a lot of pressure to publish exciting and novel findings. We have to publish, yeah? So sometimes we forget to check the replication or the quality of our data. Yeah? We sometimes overlook this replication because it takes a lot of time. I cannot publish yet because I'm not sure my data quality, you know? So it's unfortunate. That is the push for us. We need to publish. So we publish whatever data we have. Again, remember the basics. Science and statistics need to go together. If you're a statistician, you need to understand causal. So you need to work with scientists who understand maybe the basics. The scientists are looking at data, but they need to do it in a statistically sound manner. You know, not just looking at the data and say, oh, I've done it so much, I know what's going on. You know, is that statistically correct? We need to observe and hypothesize and find the causal relationships. And here was this 10 things which statistics taught us about big data. 1, if the goal is prediction accuracy, try to average. Try to use different models, different methods to reach the same result. Essentially, this is how big data is working to see that they know you, because they're looking at many convergences of results. When testing many hypotheses, correct for multiple testing. When you have data measured over space and time, smooth. And you have to do this for any environmental data. Hydraulic, hydrology, all always has to be smoothed out. When you analyze your computers, be sure to plot it. And this is a real thing that happened to me. One of my master's students, I was not the main supervisor, presented her data. And I thought the data looked a bit funny when she was showing the results for different tests. And I asked, can you plot the data? And she was doing a regression and correlation. And then when she plotted the data, it was bimodal. So you couldn't do any of the parametric tests. You know, she had to go back because everything went into the computer, which was so easy. You put everything to computer, computer comes out with a figure. But you fail to look at the data. So this is very important to plot it. I think Dr. Mahendran is a very keen advocate of this. I know. Looking at the data, plotting, making sure what it looks like, understanding what your data looks like. That's very important. So visualization is a very important tool to use. Next, interactive analysis is the best way to try and figure. Try to make big data as small as possible, as quick as possible. So that, again, look at the data, try to see what the patterns, try to remove the noise, try to remove some type of patterns in a way, or take out the patterns to try to understand why the patterns are there. Know what the real sample size is. Big data thinks that n is all, but actually it's not. Because how do they collect the data? Yeah. So, unfortunately, one of the problems with big data is that the method of collection is changing all the time. Because in a way, Google Analytics is always learning itself. So the baseline is always changing. Depends on when you collect the data. So unless you run a randomized trial, of course, you might have confounders. Yeah, things that are a little bit out of line. Yeah, I used to think correlation implied causation. Then I took statistics class. So I hope you all know that having something correlated doesn't mean A is causing or X is causing Y. It just happened to be so. But what is the real reason? So define a metric for success up front. I tell this to my students, but they often fail because they always do a correlation and say, oh, look, it's significant at this level. What actually do you want it to be significant at what level first? Yeah, quite often they do it after the fact. I found a relationship. Oh, yeah, this is significant here. Yeah, instead of first defining what level significance is really meaningful for them. And then if you do have some code, then you should really try to make it available and have some other people try to check. So we need to work in that collaborative fashion. Have your team members work with quite a number of other people. Have, like I said, the giant to try and check it for you. Because sometimes when we are so focused on our study, we're only looking at that, we're not thinking of other things outside of it. So it's always good to have people criticize you. It's good because then you have to think, did I really think about it? Did I forget to think about it? Next, also think about the problem first, not the solution backward, because sometimes we know how to do one method and we use it for everything, even though it's not suitable, even though it's not the best method. Yeah, we get so used to a tool, we don't really think about whether it's the best method. So I think those are some of the things which I hope that you can take into mind when you're doing your research. And also start to look at things outside what you would normally look at, and become like my nephew, start looking at YouTube for strange things in the universe. Okay, thank you. Any questions?
Thank you very much, Dr. Zelina, for a very interesting talk. Beginning was a bit frightening with the space noises and all those things. When she got to 42, I started thinking, the only thing that crosses my mind is 42 million, you know. So, that's the answer to some question. So, but I'm just kidding, right? Okay, was a very interesting talk, right? And I'd like to invite Dr. Akbar again, right, to the stage to present a token to a very interesting talk. Was given some directions, right, to think of in the future, right? Thank you. Right? So we are right on the dot, just about 2 minutes running behind schedule. Right? But it's okay, I mean, plus minus, we are all right. So the third talk is going to be an invited talk entitled The Extra